Okay, it's the top of the hour. Welcome, everybody. I think I'll go ahead and get started. We'll have a few people probably joining in as we go, but want to leave plenty of time for our speaker today. So my name is Jenna Bowers. I work on our payment technologies research and development team at Ingevity. We're really excited to be hosting this webinar series called Connecting the Dots. We'll be providing DOT personnel with a platform to share their experiences and successes with the newest developments in payment technologies. So we'll be hosting a few of these each year. So if you have any specific topics that you're interested in learning more about, please reach out, let us know, and we'll see if we can secure an expert in that area to give a presentation. Our next one will be tentatively scheduled in November. And we'll confirm that date and time and send more details as we get closer to that event. Today's talk is going to be recorded. It's going to be available on the Behind the Screen website, which we'll post here in this chat. It'll also get emailed to all the attendees, so you'll be able to access that. So I'd like to go ahead and present our speaker today. So we'll be hearing from Dr. Fan Yin. Fan is an assistant director at the National Center for Asphalt Technology. He obtained his PhD in civil engineering from Texas A&M University, and his research expertise includes balanced mix design, advanced asphalt material characterization, and sustainable pavement materials. He's a registered professional engineer in Texas, and we're so honored to have you here today. Thank you, Fan.
All right, thank you very much, Jenna, for the nice introduction. Good afternoon, everyone. Thank you all for joining us today for the Connecting the Dots webinar. I definitely want to give a shout out to Ingevity for the opportunity to present, about one of the study we did here. And also, I do want to mention, the name of the webinar series, Connecting the Dots, is pretty legit. I mean, it's a very catchy name, and good job on that. Today, I'm going to present a case study that we did at NCAD using warm mix asphalt at reduced production temperatures for balanced mix design. It's kind of like I mentioned in the bio that I gave Jenna, balanced mix design is something that's, one of my primary research, topics at NCAD. And I'm sure like many of you have heard about the balanced mix design and, you have recognized the benefits of doing balanced mix design. There's a lot of momentum out there among our industry on doing that, obviously for good reasons. I mean, this slide, I always like to share, the three primary benefits that, in my opinion, that balanced mix design provide for our industry. One, is obviously kind of like because of the focus on, performance testing, it gives us a better chance to improve the mixture quality and eventually, make our asphalt payment last longer. Uh, the second benefit that I like to mention here, it's the innovation potential. Because the balanced mix design focus on the end product testing rather than like specify the recipes, it does open the doors for innovation for our contractors, for our asphalt mix designers to look into like innovative asphalt materials and the locally available materials. And because of that, as I mentioned before in several kind of like webinars or presentations that I gave over the years, to me, like a balanced mix design does provide kind of like a platform for us to look at different options to achieve that performance requirement. And because of that, it also provides the opportunity to allow contractors, mix designers to really, challenge themselves and look into the different options that they can use to achieve performance. And eventually, it gives them the opportunity to optimize the cost. Because at the end of the day, we still live in a low bid environment. So, definitely the cost of the material matters. So this is kind of like where we believe like a balanced mix design provides significant benefits for our industry moving forward. And I believe like that's why like lots of DOTs have fully embraced the benefits of balanced mix design, and that's why they are doing either like the in-house research or some demonstration project to get started, or to implement balanced mix design for their specifications. For those of you who are still new to the concept of balanced mix design, I know there's lots of information out there on the internet about this topic, which can be overwhelming to some degree. I highly recommend that you start from the balanced mix design resource guide that NAPA hosts with NCAT support. This is what we would call like a one-stop shop information related to balanced mix design for our industry. It has lots of good information. It talk about the benefits, why we're doing balanced mix design, what are the different approaches. It also provides very detailed information about the different mixture performance tests that can be used with balanced mix design. We kind of like put them into different categories about like a rutting test, cracking test, and a moisture damage test. For each of the tests, we provide kind of like a one-pager summary. And also we provide a video of that test so that, you can show that to your students or technicians, engineers who are running the test in the lab just to make sure like, they understand how the tests work. And also like we're still like, this is kind of like a moving target. That means like we are constantly, updating the information on the resource guide. One big part of what we do as part of this effort is to provide the most updated implementation status. Because I mentioned like there's lots of momentum and interest among state highway agencies on implementing BMD, there's lots of information where they are, what they are doing to move forward with the process. If you go to the resource guide, there will be a section focused on implementation. This is where we provide a very detailed information on what each state is doing related to balanced mix design. And also we are providing lots of case studies showing like, if you're one of the folks that work in the lab, you got existing mix design that designed using superpave approach, let's say, and you run the performance test, realize this mix design needs some modification to improve either the rutting test or the cracking test result. What are the options that you can do to achieve that? So we did provide several case studies based on what we have done over the years at NCAT to just kind of like make those tools available to you. Like I said before, balanced mix design is more like a kind of like a buffet table. There are different options on the buffet table that can be used to achieve balanced mix design. Which one should we pick? It really depends on your materials. This is why, like, we highly recommend, state highway agencies and also contractor to start playing with those performance tests to understand like how the different mix design variables affect your, test result. Lots of people talk about adding asphalt binder, which we know works, because of the way asphalt binder, quantity affects the mixture test result. But it's not the only option, right? This goes back to the benefit of balanced mix design. It opens doors for innovation. We can look into like additives, we can look into the recycled materials or combination of all these. And that's, in my opinion, the real beauty of doing balanced mix design. So definitely want to kind of like make this, resource guide, make you guys aware of this resource guide. If you scan the QR code, that should take you to the website, and there's lots of information on that. So before I talk about, what we did here at NCAT on this case study, kind of like I want to take a step back about, want to share some background information of why we're doing that. What are the motivations? If we look at the effort that has taken place over the last several years, there are a lot of effort out there related to balanced mix design. A majority of them try to look into like how can I optimize the mixture components and the proportions to balance rutting versus cracking resistance. Okay, and if you go to TRB or AAPT or those technical conferences, there's lots of presentations talking about this perspective, which is important, right? Right now, like, we say like we have lots of dry mixer issues. That means like they have, fairly good rutting resistance, but not so much on the cracking resistance. So what should I change on those mix designs that can give me the balanced performance, which is definitely an important part of what we need to figure out for our industry or for our community moving forward with BMD implementation. When balanced mix design was first established, a majority of the discussion at that time was focused on mix design. It's kind of like, in the lab scale, how can we put together the job mix formula that have the balanced performance? There was really not much, discussions or information on production. But later, like as we progress through the implementation process, we realize, when we talk about balanced mix design, production also matters because that means like not only we need to make sure like the mix design have balanced performance, but also we need to make sure that the final plant produced mixes also remain balanced. Because at the end of the day, it is a plant produced mixer that's going to be placed in the field that's going to decide how long the asphalt pavement is going to last, right? And we know like there are some changes that could happen, from the mix design phase to the production phase. So that's why, like right now, when we talk about the balanced mix design, even though the name only shows kind of like the mix design phase, but definitely production should be a major, another important part of the balanced mix design framework. When we talk about the production, there's different variables related to production that can affect the balance mix design. I think like recycled materials management, how you handle the wrap or rest, could affect the test results of your plant produced mixes. Other variables include like a silo storage that can be another example. The topic of the case study that we did, that's the topic of today's presentation, is really on using warm mix asphalt technologies. Uh, if we look at our history of using warm mix, at least in the United States, we have a fairly successful history over the last 20 years. I went back to look at the most recently released NAPA industry survey that shows like about 175 million tons of asphalt mixtures produced in the 2022 construction season were produced with Warmix technologies. And then if we dive deeper into those numbers, a significant amount of that 175 million tons of mixtures with Warmix asphalt technologies were kind of like were produced with Warmix technologies using as compaction aids. So in that case, what we really mean by saying that is that they add those technology into the mixture, but they did not necessarily reduce the temperature. So in that regard, like that's why some people call this technology as a compaction aids. So you do have those chemical additives or foaming, technologies as part of the production process, but temperature pretty much remains the same as the hot mix control option, if you will. But when we look at the kind of like what I would call like the true warm mix asphalt, this is where like we can significantly like reduce the production temperature of the asphalt mixtures. This is kind of like where the whole idea of a warm mix was first generated, and there's lots of great research and demonstration effort from Europe on using like a lower production temperature for warm mix asphalt. And when we talk about like a lower production temperature, personally, I feel like 50-degree Fahrenheit or more could be a pretty good target on that. And because of the reduced production temperature, and we believe like that has the potential to provide some performance benefits related to BMD, mainly as a result of the reduced asphalt aging. We do know that when we produce the asphalt mixture, because of the high temperature that the asphalt binder is going to be exposed during plant production, there will be a significant amount of aging that occurs within the material. And we know that asphalt aging has an impact on mixture performance, especially on the cracking and the durability perspective of the performance. So if we produce the asphalt mixtures at a lower production temperature, and then by doing so, we can reduce asphalt aging. That should have the opportunity to allow us to, improve the cracking resistance or the durability of the mixture. So that's kind of like a really, the motivation of this case study that we did at NCAT, and that's the study that I'm going to share more results and findings with you today. So with that being said, the research objective of today's presentation or the study we did was really to answer the question listed here. What happens when like a true warm mix asphalt meets balanced mix design? And then what we did is kind of like to start from a lab case study to explore the feasibility of using like a lower temperature warm mix for balanced mix design. And I do want to mention the case study that I'm going to share with you today was the same paper that we published like last year at AAPT annual meeting. So for those of you who attended last year's AAPT meeting, I apologize that you have to listen to me again today. But hopefully, like at the end of the presentation, I'm going to provide some new information that was not covered in that WAPT presentation. So regarding the case study, it's pretty much like a three-step process on what we did as part of that effort. First, to start with the study, what we did was to, talk to a local asphalt contractor. We get a super pay volumetric mix design. This is kind of like our starting point, if you will. And then like we did ideal CT and high temperature IDT test because those are, the two performance tests that, Alabama DOT allows for their, local roads BMD specification. Balanced mix design is a framework. There's different approaches that has been used by different agencies for implementation. But for the local roads, the special provision that the ALDOT has for these kind of like, county jobs, they use approach D, which is where like, it's almost like a fully relax or eliminate those volumetry requirements. Instead, all the mix design requirements are going to be based on performance testing. As I mentioned, like a high temperature IDT, which is kind of like their PICS rutting test. And then on the cracking side evaluation, they decided to pick the ideal CT. So with high temperature IDT and ideal CT as a testing combo, they want to make sure like the final approved mix design is going to have balanced rutting and cracking resistance. And also I included the criteria that they have, for their provisional specification, just to give you some numbers when we look at the high temperature IDT or the ideal CT test. The only recipe requirement that the specification has is that they do have a minimal requirement on the maximum aggregate size and also the carbonate stone contacts. So the reason to specify the carbonyl stone contact is to make sure like the mix design going to have a good friction resistance. When we talk about the balanced mix design focus on rutting, cracking, or moisture evaluation, those are what we would call like a performance side of the evaluation. But also like, the safety perspective is something that we should also like, emphasize and incorporate. And that is why like in this case, ALDOT decided to keep the carbonate stone content as a requirement in their BMD spec, just to make sure like the mix design is still going to have good friction numbers when used in the field. Now coming back to the kind of like the flow chart that I'm showing you now, as I mentioned, we start from the super pay mix design and we did ideal CT and high temperature IDT testing to see like where the results fall as compared to the specification criteria that I showed you earlier. And then based on the testing data, we realized that the mix design did not pass ALDOT's BMD specification, which was really not surprising to us because we do have quite a bit like dry mixes here. They have good rutting resistance, not so much on the cracking, and that's exactly what we saw on this mix design. And because of that, we need to do some BND modifications to the mix design so that we can pass both, the high temperature IDT and ideal CT result. For the BMD modifications, we look at two different approaches. One is just to like add asphalt binder. As I mentioned before, it is one of the approaches that can be used. Lots of people talk about like, we have dry mixes. That means like we do not have enough asphalt binder. So in that case, if I add asphalt binder to improve the asphalt binder quantity, that should have helped me improve the cracking resistance. So that's pretty much like the thought process we had for that modification approach. The other approach we decided to do in this case study is to use warm mix use a true warm mix asphalt with the reduced temperatures. So like I said earlier, that balanced mix design is a buffet table. There are different options that on the table that can allow us to get to the performance, meet the performance requirement. And in this case study, we decided to look into using lower temperature warm mix. And because of the discussion that I just shared with you earlier, if we reduce the production temperature, that should reduce the aging that occurs in the asphalt binder. And because of that, it has a potential to give us a more balanced, performance, especially on the cracking and the durability side of the performance. After we did the BMD modifications with those two approaches, we went back to verify or to test the ideal CT and high temperature IDT, and to still like compare with outdoor specification to see like do we pass or do we still need to go back to make further modifications. Once we passed the BMD specification, and then we did some additional testing. On the left side here, as I try to highlight with my pointer here, we did a modified overlay test because we want to kind of like go beyond the ideal CT, which is an index test, right? And we want to answer is like, when I got, improvement in the CT index, let's say like 10 units improvement or 20 units improvement, how does that affect the pavement performance? This is where like we decided to incorporate the overlay test that allow us to determine the fundamental fracture properties of the mixture by doing the modified overlay test. And then we can use the test result to do some like ME simulations so that we can make a connection between mixture quality versus the pavement performance. And I'm going to provide more information over the next few slides. And also, what we did in the case study was to look into extracted binder testing. We added this part of the evaluation in the case study because like when we test like the asphalt mixtures, we try to capture the combined impact from asphalt binder quantity and asphalt binder quality, right? We know like the amount of asphalt binder matters in terms on the mixture performance, but at the same time, we know the quality of asphalt binder also matters. So when you run the ideal CT or high temperature IDT or any other mixture test, you cover the combined effect of the two. It's really hard to separate, what part of the performance comes from the quality side, which part comes from the quantity side. But if we do the binder testing, that gives us the opportunity to kind of like isolate the two impacts. Pretty much when we do binder testing, we're going to focus on the binder quality evaluation because it's more telling us, the rheological properties of asphalt binder that can be extracted from the mixture. So that's the reason why we decide to include the extracted binder testing to help us understand, how the different BMD modifications work and how they improve the ideal CT results on the cracking side. So now moving on to the experimental plan, as I mentioned earlier, we grabbed a local mix from one of the contractors that we have a good working relationship with at NCAT. It's a 12.5 millimeter super paint mix with 20% wrap and PG 6422 binder. Nothing really like unique about this mix design. This is one of the mix design I would consider kind of like as an everyday mix in Alabama or in many parts of the Southeast United States. One thing I do want to mention here is regarding the wrap. The wrap we tested as part of this mix design has a PG 105. Okay, I know this number may sound like intimidating to many of you, especially those like from the northern states. But this is something that we are saying on a regular basis, kind of like in this part of the country. I know like 10 years ago, about 15 years ago, when we look at, the local wrap, the PG grade was around like a 90 to like maybe 94, around that numbers. But the more recently, like the sample that we have collected over the last couple of years, they are all, fluctuating around like a PG 100 to PG 110 degree. So the wrap is getting stiffer. And that's something that we just need to be aware and how we can. I mean, there are different ways that we can do from the mix design perspective to kind of like overcome the stiffening impact from the wrap. But just want to kind of like to provide that information out there. The mix design has 5.2% asphalt content, 14.7% VMA at 60 gyration. Everything looks like pretty normal for a super pay volumetric mix design. And when we did that, kind of like as a baseline testing, with the high temperature IDT, we got a very good number. That means like the mix have excellent rutting resistance. But when we test ideal CT and compare the result against what adults has in their BMD specification, this is where we realize, you know what, this mix does not have adequate cracking resistance. It goes back to the earlier discussion that I had about the dry mix issue. So this is kind of like, the mix design we have. And then the two BMD modifications, as I mentioned earlier, the first approach is add asphalt binder. And because we are not changing, all the other mixture components or production conditions, we pretty much refer this approach as a hot mix approach. So in this case, all we are doing is add a virgin binder, try to improve the test result of the mix design. The other approach is what I would call a warm mix approach. This is where we use the chemical additives, add into the mix, and because of the chemical additive that allow us to reduce the mix production temperature. And then depending on the results, and then we add more virgin binder as needed in order to achieve, the balanced mix design criteria that I mentioned. I'll provide more, detailed results over the next slide, but those are the two balanced mix design approaches we did. Since the whole idea about what I call a true warm mix asphalt is, lower the production temperature, I just want to share detailed information about the mixing temperature and compaction temperature that we used in the study. For the hot mix option, the mix design, all the specimens were mixed at 315 degrees Fahrenheit, and the condition for 2 hours at 275 following the Asphalt R30, and then compacted at 275. For the warm mix option, this is where I mentioned because of the chemical additive that added into the mix, allow us to drop the temperature from mixing from 315 to 255 degree Fahrenheit. So that's about a 60 degree Fahrenheit reduction on the mixing side. And then because of the reduced mixing temperature, we also lower the conditioning and the compaction temperature for the mix. And also we followed, the Asphalt R30 recommendations for the conditioning temperature. We reduced the temperature from 275 to 240. And then, after conditioning, we went straight into the compaction. And we did not get into any compaction issues with the low temperature, but that is because of warm mix additive that we added into the mix. So now I just want to get into some of the test results that we got in the case study. I want to start with the hot mix BMD modification option. So the first thing we did was, as I mentioned, the starting point at volumetric optimal binder content did not have adequate cracking resistance. So this is kind of where the data point falls on these ideal CT charts. So the blue dots here is where we started at 5.2% AC, total binder content. We got a CT index a little bit above 25, where the criteria is 55. So we are, pretty far from, the target. And then for this option, for this BMD approach, what we did was to, add asphalt binder into the mix, try to improve the result. We look at the multiple asphalt binder content, as you can see here. We started from 5.5%, went all the way to 6.1%. And as you can see from the chart, adding asphalt binder definitely was effective in improving the CT index or improving the cracking resistance of the mix. It was about 5.9% AC, this data point that I tried to highlight here, that we finally got to the mix design kind of marginally passing the CT index of 55, and that's what Aldot used for their BMD specification. So if you look at this binder content, 5.9%, and compared to where we started, 5.2. So we're saying in order to pass the cracking test requirement for this specific mix design, that we have to add a 7/10 more asphalt binder into the mix, which is pretty significant if you ask me. But the one thing I want to mention here is how much asphalt binder you add or how much modification you do on mix design to achieve balanced mix design. It really depends on where you start with. If your starting point is pretty good, pretty balanced, then you probably don't have to make much modifications. But if you're far away from the target to start with, then that may require fairly significant mix design modification. And apparently, this is the case we had here. We have to add a 7/10 mole binder to pass the CT index. And also after we got to the CT index number passing, we went back to test high temperature IDT just to make sure like we can still meet the writing requirement. And based on the result, writing should not be a concern. So at 5.9% AC, this is where like we kind of like move the data point into the balance spot where we can both pass the high temperature IDT and also ideal CT. So this is the hot mix modification option. The second option we did was using the true warm mix asphalt at reduced temperature. To start with, what we did was kind of like keep the binder content the same, but only reducing the production temperature. As I mentioned earlier, we dropped the mixing temperature by like a 60 Fahrenheit and reduced the conditioning and the compaction temperature by like a 35 So because of that change, if you look at these two data points, we were able to improve the CT index number from like maybe like a 27 to like a 39, kind of like a 10 to 20 unit different depending on which warm mix additive we used in the study. Even though like it improved the number, but it was still not good enough to pass the 55, minimum CT index that RDOT has in their specification. And because of that, we have to keep adding more virgin binder into the mix. So with that being said, it's almost like a hybrid modification approach, if you will, because we started adding warm mix additive, and then we add additional virgin binder on top of it. So it's like a hybrid approach that allow us to get passing the CT index. And if this is the result for one of the warm mix additive that we tested in the study. In this case, it was about like a 5.6% AC that we were able to move the data point north of the 55, threshold here. And in this case, we went back to verify the high temperature IDT to make sure like it still can pass the high temperature IDT test to make sure it still can good writing resistance and everything looks good. And then in that case, we said like, well, for this modification approach, our binder content going to be like a 5.6% on the performance side. So if you compare where we started, 5.2, we got 5.6. In this case, we're talking about like a 4 times more virgin binder that need to be added into the mix to make a super pay volumetric mix balanced. 4 times is still a lot of binder, but if you compare to the first approach we did, that was a 7 times. So the difference is pretty, significant if you ask me on the two modification approaches. When we finish the ideal CT testing, this is something that we have been looking as kind of like a pretty normal practice at NCAD is to look into what we call like ideal CT interaction diagram. When you run the test, you get the CT index number, which is the final parameter. But there's a lot of other information that we can learn from the kind of like the low displacement curve of the test to give us a better understanding of how the mixture behaves under indirect tension. So this is kind of like how we develop the interaction diagram analysis. Pretty much what we did was we plot the fracture energy on the y-axis against the post-peak behavior parameters from the test on the horizontal axis. And then like the diagram include a series of what I call like a contour curves. Those are the equal CT index contour curves. So pretty much like all the data points on the same curve, they have the same CT index number, but they could have different fracture energy versus the L75 divided by the M75. So it is kind of like the combined impact of mixture toughness versus mixture brittleness that controls how the mixture reacts to ideal CT in terms of cracking resistance. So what I'm showing here is kind of like the hot mix control mix where we started. This is kind of like the volumetrics mix design that we started on this case study. And then the 3 balance mixes after BMD modification. The orange data point here is using the hot mix option, and then the two data points here are using the warm mix option. So as you can see here, we definitely were able to improve the CT index number. But if you look at the interaction diagram, it was pretty much like we were improving the post-peak behavior of the mixture. So the improvement in CT index by looking at the interaction diagram here tells us we are improving kind of we make the mixture less brittle, make it kind of more flexible, and that is where we can improve the cracking resistance. So just kind of some side discussion related to ideal CT, we do believe they provide lots of good information other than just looking at the CT index. But if you look at kind of the three BMD mixes, they are pretty much on the same, CT index contour, even though the hot mix option, the mix has 3 times more virgin binder as compared to the two warm mixes that we tested in the study. As I mentioned, after the high temperature IDT and the ideal CT testing, we did the overlay test, try to look into a different loading condition. Ideal CT is a monotonic loading, but with the overlay test, we are applying the cyclic loading condition to the mixture to give us a different perspective on how the mixtures react in terms of cracking resistance. For the overlay test, we follow the Texas methodology, but modify the maximum opening displacement to a smaller number that allow us to get more cycles from the test so that we can, obtain some fundamental fracture parameters from the test. In terms of the index parameter, we look at the number of cycles to failure and also the crack propagation rate, which is kind of a relatively new parameter that TxDOT has implemented, mainly try to reduce the variability of the overlay test for data analysis. So for the number of cycles to failure, a higher number is desired for better cracking resistance, but for the crack progression rate parameter, a lower number is desired for better cracking resistance. And then, as I mentioned, because the cyclic loading and the reduced maximum opening displacement, it gives us the opportunity to look into the Paris law fracture parameters that we can get from the test, so that we can use the test result put into ME simulation to predict how the pavement is going to behave in terms of the cracking performance, rather than just focus on the mixture quality evaluation. So if we look at the test results, on the left side is the overlay test, overlay number of cycles to failures. The first bar I shown here is the hot mix control. This is where we started on the volumetric, mix design. And then the next one is the BMD, but using the hot mix option. And then the other two are the BMD mixes using the warm mix options. As you can see here, overall, no matter which approach we did with BMD modification, we were able to improve the number of cycles to failure. And that's kind of the same story that we saw with ideal CT testing. And then if we look at, the crack progression rate parameter on the right side, we saw the same trend. We were able to reduce the numbers here, indicating better cracking resistance. Interestingly, if you look at the difference between the BMD hot mix option versus the BMD warm mix option, we saw the improvement from BMD modification was slightly more pronounced for warm mix than hot mix. This is something that we did not see with ideal CT testing, but we saw in the cyclic loading, and I think that can be attributed to the different loading condition with the test. As I mentioned before, when we do the index test, we got improvement on, let's say, a CT index or number of cycles to failure from the overlay test. We know we should get better cracking resistance on the mixture side, which is good. But many of you, including myself, always wonder, what does that mean in terms of pavement performance? If I place the two mixes in the field, are they going to perform similarly or are they going to perform differently? So this is why, with the overlay test we did, we were able to use the Paris law fracture, property parameters from that we got from the test result and put into simulations to understand how the pavement is going to react under different traffic and underlying pavement conditions. So for the ME simulations, we use a Texas asphalt concrete overlay design system. For pretty much it's focused on the overlay design applications. And then for this simulation, we focus pretty much on reflective cracking without considering like a top-down cracking or thermal cracking. That's kind of like what the software was developed for. For the simulation, what the parameter we look at is the what we call like a reflective cracking rate. Basically, it just talk about the number of cracks of the overlay compared to the number of cracks in the underlying layer, and that number is expressed as a percentage. So I'll give you two extremes. If we have 0%, that means like we have no reflective cracking. Or if we have 100%, that means like all the cracks in the underlying layer has been reflected through the asphalt surface. So this is kind of like where we got 100% reflective cracking rate. For the pavement structure, we did a 2.5-inch overlay over existing asphalt pavements. And when we did the simulation, the variable that we play with, it's the A and N parameter that we got from the Texas overlay test. And pretty much like we simulate the different overlay mixes, but keeping the underlying structure and traffic climate condition the same. We did look into different combinations of traffic and underlying layer conditions. We look at the 3 mini ESOLs over 15 years, or kind of like another a situation with much higher traffic volume. In that case, it's 10 mini ESOLs. In terms of underlying layer, we look at like a low severity cracking in the underlying pavement layers versus medium severity cracking. So just like different scenarios to see how the surface mix reacts to those pavement structures and underlying conditions in terms of reflective cracking performance. We got lots of results from the simulation, but for the interest of time, I'm only going to show you like a quick example here. This example here correspond to like a 3 mini ESOLs in terms of the design traffic, and also like using like a low severity cracking in the underlying pavement layer before we apply the overlay. And then the plot showing here, it's pretty much like the predicted reflective cracking rate development over time. There are 4 curves here, kind of like the 4 mixes that we evaluate as part of the case study. The blue curve is a control hot mix. This is where we just take the volumetric mix design, did nothing other than just to characterize the properties and to run the simulations. And then the other 3 curves are the one that we did B&B modification. The orange is the hot mix option, and then the gray and the yellow are the 2 warm mix options. So if we use let's say like a 50% reflective cracking rate as our criteria to define the failure life, if you will, of the overlay, in this case, if we look at the control hot mix, it is about like a 9 years, right? This is, takes about 9 years for the crack, for 50% of the cracking in the underlying layer to reflect through the asphalt overlay. So that's where kind of like we put like a 9.2 as the lifespan, if you will, in these specific conditions. And then we did the same thing with the 3 balanced mix design mixes. And in this case, for the hot mix option, the lifespan increased to 12.6 years. And for the 2 warm mix options, we were able to extend the lifespan to like a 13 to 14 years. So if you look at the difference between those numbers compared to where we started on the blue curve, that is kind of like the overlay life extension that we got by doing balanced mix design. Okay, so that definitely answered the question I asked earlier. We got better index parameter from ideal CT or from the overlay. What happens if we put those mixes in the field? So I think this is definitely a good simulation case study showing like the life extension benefits of balanced mix design. So in general, no matter which combinations of condition we play with in the simulation, we always saw like a B&B modification give us longer overlay life. But the life extension varied quite a bit from 1 year to 5 years, depending on many factors, which balanced mix design approach we're using, and also the traffic and underlying layer conditions. So This is something that we need to keep into consideration when we try to tie the mixture performance to pavement performance, because there are some external conditions that could affect how the pavement perform in the field. We also did extracted binder testing, as I mentioned, try to understand, what happened to the extracted binder properties. And I know there's lots of data in this table, but overall, like when we test the extracted binder, we found out that by doing balanced mix design modification using both hot mix option and warm mix option, we introduced a softening impact on the extracted asphalt binder, but that impact was much more pronounced for the warm mix option as compared to the hot mix option. If you look at the high temperature number that I tried to highlight here, this is where we started, 85.7. With the BMD hot mix option, that number dropped a little bit, but not so much. But if you look at the two warm mix option, this is where we caused like a significant reduction on the high temperature end, and we saw the same thing on the lower temperature end. And that has a lot to do with the reduced aging that I mentioned, related to how we condition the loose mixtures before we do the compaction. So this is just kind of like from the binder, property perspective, shows like how reduced temperature affect asphalt aging, and eventually that improves the ideal CT and overlay result that I showed you earlier. In addition to the PG, we also look into like the master curve analysis, including like Glaver roll parameter and the delta TC parameters as a function of PV aging. I'm only showing the Glaver roll parameter result here. Shows how the results change as a function of PV aging. And if we use like as a 600 kPa as a cracking criteria for the Glaver roll parameter, that can tell us like how many PV hours the different binders can endure before it reach that. It's almost like aging tolerance life for the extracted binder before it reach a cracking threshold number with Glaver roll parameter. As you can see here, when we look at the hot mix control, it takes about 15 hours in the PEV. With the BMB hot mix option, that number increased a little bit, but not so much, like increased to 18 hours. But when we look at the warm mix option, this is where we saw significant improvement. So what we are saying here is that when we do like a warm mix modification, we are improving the quality of the asphalt, overall asphalt binder in the mixture, and that definitely contributes to the improved cracking resistance on the mixture side. We saw the same findings for the delta TC parameter, but for the interest of time, I'm not showing the results here, but those results are in the paper that we published with AAPT. So a quick finding, what we learned from the study, when we did the BMB modification, we got a more balanced performance test result. On the cracking side, we got improved cracking resistance in ideal CT and overlay test. We did see like a reduced rutting resistance, but they were still able to pass the adult specification. So that's why we said like reduced, but as still adequate. When we look into like what really caused the improvement in cracking resistance, for the hot mix option, it was pretty much what we did was to improve the binder quantity by adding 7/10 more binder. Not so much on the change of the binder quality. It was more about to give a high volume of asphalt binder into the mix. But when we look at the warm mix option, it's a combination of increased binder quantity because we're adding 4/10 more binder into the mix. But also we were able to improve the binder quality because of the reduced aging and brittleness of the binder. So it is a combination of the binder quantity and the binder quality that give us the improvement on cracking resistance. From the simulations, we learned that BMD modifications was able to provide life extension benefits, and that benefit could vary depending on the traffic and underlying layer condition. So if we can make the payments last longer, the life extension benefit could justify the cost of the BMD modifications by adding more binder or adding additives upfront, from the life cycle cost perspective. So now answer the question I asked earlier, what happens when warm mix meets balanced mix design? I think the short answer is yes, it works, but we definitely recognize there's limitations. We did only one mix design. When we did the cracking test on the mixture side, we did not consider long-term aging. When we look at the simulations, we focus on overlay project. You may wonder what happens with new construction projects. And more importantly, this is a lab case study, and what happens when we run the material through the plant. And that's something like we did not incorporate in the scope of the work for what we did. But the good thing is that we were able to get NRA sponsor kind of like a follow-up study to look into the field validation. And for that field validation work, we partner with Ingevity. We're trying to do like two field case studies, one in Virginia, the other in Missouri. The Virginia project, the production has been completed, and we are working on the testing. And for the Missouri project, we are in the process of finalizing the mix design and awaiting for production to take place. So stay tuned for this NRA project. We are very excited about, kind of like upscale our case study from the lab to the field. And, hopefully, when we're getting close to finish the NRA project, we'll be glad to share, more results from what we learned on these two field studies. So with that, I will thank you for your time and attention, and I will hand it back to Jenna to see if there's any questions or comments from the group today. Thank you.
Thank you, Fan. That was great. Excellent presentation. We have some time for some questions. And so if you have one, there's a Q&A function at the top. If you want to write, you can write in your questions there, and I will share those with Fan to answer.
Yep.
While we're waiting on some of those, I do have a question for you, Fan. Since this is a lot of DOT personnel, Warmix sounds like a useful tool for contractors to meet BMD requirements. Just curious what your thoughts are on how an agency or what an agency can do with this information that you just shared with them today.
Yeah. Yeah, that's a good question. I think as I mentioned in the presentation, warm asphalt technology is nothing new to our industry, including DOT folks. But the interesting part is like lots of the specification are set in the way that does not specify like how warm mix are used. When you add the technology into the mixture, do you still count that as warm mix or it's hot mix? Obviously this case study definitely shows like when we try to do the true warm mix with the reduced temperature, it provides a performance benefit. But on top of that, that also provides like environmental benefits. And I think that's something that's is very important as our industry move towards like net zero carbon emissions. So I mean, I highly suggest the DOT is considering not only just saying like allow or using warm mix, but also like specify how warm mix should be used, specifically on the temperature side. I mean, personally, I'm a big believer of the reduced temperature, and like I said, the case study definitely provides very promising result on the lab scale, and we'll see how the field studies turn out. But I'm very optimistic at this point. So.
Great, thank you. It looks like so the Q&A function may or may not be working correctly. So if you want to throw some questions in the chat, that's okay too. Also, if it's too lengthy really to try to write, if anybody has a question and wants to raise their hand, we can certainly unmute you for that if you want to ask that question. It looks like there is a couple of them that are now working in the Q&A. So Fan, one of the questions is why you decided to work on ideal CT and HD IDT to assess the BMD performance and not any others.
Yeah. Oh, like I said, I mean, this is kind of like a case study we did based off ALDA specification, and Alabama DOT, like as I mentioned during the presentation, like the way they set up this specification for local road projects is using ideal CT and high temperature IDT. But obviously, like I said, in the presentation, that different DOTs are using different tests. The two field study that I mentioned as part of the NRA work, we are working with Virginia contractor there. And in that case, we're doing ideal CT, APA, and Cantabro because that's VDOS BMD testing combo. But for Missouri, we are looking at ideal CT and Hamburg and ideal RT because that's what Missouri is doing. So I guess we picked the test based on which specification we try to follow on the case study, and we try to follow that state specification practice. So.
Thank you. It looks like another question is, I want to ask, in your opinion, the use of Warmix can enable higher wrap content?
Yeah, I mean, I think this is a good point. If you think about, the reduced aging and with the improvement on the cracking resistance, I mean, it does have the potential to allow us to use more recycled materials because like we got additional buffer on the cracking side or the durability side that could allow us to use the wrap. This is something that we have not, looked into like in the case studies, but that's definitely something that should be looked into. If we look, I mentioned like a carbon zero, net zero carbon emissions, using more wrap and using lower temperature are the very effective ways to do it. Can we combine those two together? I think there's definitely, the potential out there, but it just kind of, I couldn't comment much on that because we haven't done looking into like the two approaches combined, but I think it has a potential out there. So
You. Let's see, we got another question about thanking you for a very good presentation. In the future, how can we take the LCA and LCCA analysis into consideration during the application of Warmix?
yeah, that's a good point. I think every time we talk about the LCA or LCCA, we need to include the user face, which is something that we don't have the data, the kind of like the most accurate data to make those kind of judgment. In the case study we did, we have to rely on simulations to give us that, life extension benefits, and we could go back to do the life cycle cost and life cycle assessment. Ideally, when we do LCA or LCCA, we will need the field performance data, but that does take time to generate those long-term field performance data. But in the short term, maybe some of the simulation results can be considered to make sure like we're not just focused on kind of like the cradle to gate, but also include like the user phase to make it like a extended, a framework to consider the cradle to grave uh, type of evaluation, not just on the cost side, but also from the environmental impact side. So.
I think this relates to another question about, adding that, I think it was 0.7% added AC. That's going to greatly increase the cost, as well as just adding AC and maybe a Warmix additive as well. So
Yeah.
how can agencies really justify doing that?
Yeah, I mean, this has to rely on the life cycle cost analysis. Like I said, in this case, the two modifications require either adding binder or adding additive. In both cases, it's gonna increase the material cost up front. But like I said, if we can make the payment last longer, then the performance benefits that we got from there could be able to justify the material cost. This is where like we're going to look into from the field study we are doing to consider the life cycle cost analysis. How much cost effective that's going to be. That's something that we need to find out. But at least as a minimum, I highly recommend when we talk about those BMD modification, we should not just focus on the material cost upfront, but also consider kind of like the whole life cycle assessment.
Thank you. Let's see. So one of them was curious. One of the questions was curious about the Warmix additives that were used in this study.
Yeah. In this case study, the lab case study, we use two Warmix additives. One is Eversum M1, and the other one is Eversum P25. For the two field studies, we're going to use Eversum product, but it's going to be a little bit different formulations. So.
Okay, I don't see any more questions coming in. It looks, and we're at the top of the hour now. So if there's any more, if you put them in the chat, we can come back and follow up with answers to those. So I just want to thank everybody again for joining our webinar today. I want to thank you, Fan, for your time presenting. It was an excellent presentation. And we, again, will send out the recording of this and also try to get some of these answers to some of the questions that are coming in last minute. We'll get some of those answers back to you. So pay attention to another announcement coming probably in November for another Connecting the Dots webinar, and hopefully everybody can join then as well. So thank you all very much. Thank you, Fam.
All right. Thanks, Jenna. Thanks, everyone.
Okay. Take care.